In the last video, I introduced to you this really cool method called Newton's method that allowed us to approximate roots of functions. And particularly, that's going to help us with functions that we didn't have tools in order to find the roots of. But in this video, I wanted to show you just how good of an approximation Newton's method gives. And what we're going to do is we're going to approximate the square root of 5 using Newton's method and compare what we got to a calculator. So why don't you pause the video and try to use Newton's method to approximate the positive square root of 5. And I'm going to let my initial guess be 2, so you can have your initial guess be 2 if you'd like as well. All right, assuming that you've given it a go, let's do this. Let's apply Newton's method. We said that our initial guess, we're going to let our initial guess be 2, okay? And why 2 real quick? Well, I know the square root of 5, the positive square root of 5, is somewhere in between 2 and 3. I know it's 2 point something. So I thought 2 might be a good kind of whole number to deal with, so we chose 2. Now, let's apply Newton's method on this and see what we get. So we'll let x sub 1 be equal to, and we just fill in our formula here. So we have 2 minus f of 2 over f prime of 2. And just real quick, before we go along, we are letting y be equal to f of x, and f of x is going to be x squared plus x squared minus 5. And then according to this, we also need some derivative information. So f prime of x is going to be 2x by the power rule. So now all we need to do is find what f of 2 is and what f prime of 2 is. So this is going to be equal to 2 minus f of 2. So that's 4 minus 5. That is negative 1. Negative 1 in this numerator here. And then f prime of 2. That is 4. So we get x sub 1 is equal to, this is 9/4. 9/4. So we just applied Newton's method. And what happened? What happened? Well, graphically, here's what happened. So we took 2. And again, Newton's method is making a tangent line and then finding its x-intercept. So we made a tangent line for this function x squared minus 5 at x is equal to 2. So we made a tangent line here. And maybe it looks something like this, okay? That is not perfect. We made a tangent line, okay? And then we found the x-intercept, and the x-intercept was 9/4. So right there, that's x sub 1. All right, and now let's apply Newton's method again. So we're gonna make a tangent line for this function at now x is equal to 9/4. So let's do that, and we'll have our next guess. We'll have x sub 2 be equal to, and just applying Newton's method, we have 9/4 minus f of 9/4 over f prime of 9/4. Okay, and then let's find out what this is. So we have 9/4 minus, and then in our numerator, f of 9/4. So that's going to be 9/4 squared, which is 81/16. So we have 81/16 minus 5. And then in the denominator, we have 9/4 times 2, so that's 9/2. 9/2 in the denominator. Cleaning this up, let's see. We can get common denominator of 16, so that's 81 minus 80, so that's 1/16. So we have 9/4 minus, in the numerator, we said 1/16, okay? And then, actually, let me rewrite this, because we'll just flip the fraction right away. So we have minus 1/16 times 2/9, okay? That's there, times 2/9, and that's going to be 16 times 9 is, let's see, 160 minus 16, so that's 144, and we have a 2, so we're going to get 9/4 minus 1/72, I believe. 1/72, and then looks like we can multiply this guy by 18. 18 times 9, so that's 180 minus 18. That is going to be 162, so that's 161. I think this is 161/70, all right? And now that is what we get for x sub 2. And then let's see here. let's apply Newton's method again. So let's apply Newton's method again. So we have x sub 3 is equal to, and now we're going to use what we found for this x-intercept. So we have 161 minus 161 over 72 minus f of 161 over 72 over f prime of 161 70 Okay, and I definitely can't do this in my head. So this I actually calculated beforehand on my calculator, and I got 2.23606797978. Okay. So now again, we want to compare what we got with Newton's method down here with what we get on a calculator. So let's make a quick table. I want to talk about something cool about Newton's method. So let's make a table. This is going to be our nth guess, our number of guess. So, and then this is going to be what we got for our x-intercept under that guess. So this is our first guess here, which we denoted with a subscript of 0, and we got what? We said that our first guess was 2, and then our second guess, switch to pink, our second guess we said was 9/4 in decimal form, that is 2.25, and then our third guess we said was, this is our x-intercept, this is what we got from Newton's method, and that's at 161 and I calculated that out on a calculator and got this. I got 2.236 and then 6 ones. 1, 2, 3, 4, 5, 6. Okay, and then lastly, what we got out of Newton's method was this: 2.23606797978. Okay. Now, what did I get on my calculator? My calculator told me this. So this is calculator. The square root of 5 is 2.236067977. That is all the digits my calculator gives me. So, again, one thing I want to note, I actually did some research on this to get a concrete answer for you on what this is, because I saw a few different answers. And the paper said that for each use of Newton's method, the number of newly accurate digits will roughly double. So here's what that means. Here's our calculator. Here's what that means. So under our first guess here, we had how many digits match? We had 1. And then how many new digits did we get from applying Newton's method? So we had that one from our initial guess, and we got 1 new digit that matched our calculator. We have 1 there. And then applying the same process, we already had these guys that matched, our new digits that match, these 2 right here. And then doing this again, these are what we had from before. And how many new digits matched? Well, we have a 0, a 6, a 7, a 9, and a 7. So 1, 2, 3, 4, 5. So again, you could see this. For every use of Newton's method, the number of newly accurate digits roughly doubles. So that's what you can see here. And again, what is all this to say? Well, I wanted to give you some practice with Newton's method, but also show you just how good of an approximation it gives. So in the next video, we'll get some more practice with Newton's method.